Hi, this is Tim Malloy with the last video. 4-3 on RL circuits, number 11. So at the moment, T equals 0, a 28 volt battery is connected to a 5 mH coil and a 6 ohm resistor. And then I went ahead and drew our circuit here. So it starts with our voltage source. Current first travels through Mr. Solenoid, and then after that, this resistor. So part A asks, immediately thereafter, how does the potential difference across the resistor compared to the EMF across the coil? So once current starts flowing, our solenoid is going to resist the flow and I say like absorb current. But you know, inductance is resisting change in current. So this solenoid is going to be resisting the change over here while the resistor gets the scraps of that at the beginning. So in the resistor, it's 0. In the coil, it's the full 28 volts. So then B asks what happens after several seconds later. And that's when the coil is done with its shenanigans. It's not resisting the change in current anymore. So now it just acts as a regular wire. So we got our full 28 volts in the resistor, and then just nothing in the solenoid 0. Okay, pretty easy part A and B. C asks, is there an instant at which these two voltages are equal in magnitude? Now, well, if resistor starts at 0 and rises to 28, and the coil goes down to 0 from 28, then, and we know that this process is gradual, it doesn't just flip instantly, then yes, solenoid will slowly allow more current through. So before we move on, let's check. Everything's all good here. Now we move on to part D, which asks when these two voltages are equal, and if there's more than one time. So this is pretty simple with this voltage formula that we use when an RL circuit has just been closed and is quote charging. So we have our V at the selected time equals V initial, and then times this complicated 1 minus e to the negative t over time constant equation. So we solve for t pretty simply. Just put our inductance of that solenoid over the resistor. We know that, again, because the process is gradual, that when the resistor and the um, solenoid are at half the total voltage, 14, then they're equal. And then times 28, plug in our time constant. And then we multiply our time by 1,000 to put it in milliseconds. So we get 0.577 milliseconds is the time at which both the resistor and the solenoid measure 14 volts across. So that's all good there. And then part E asks, after a 4.3 amp current is established in the resistor and coil, and so in the circuit, because you know, everything's in series, the battery is suddenly replaced by a short circuit. Answer question A and B of that. Which is it? Oh, sorry. So what is the resistance or what is the voltage and the resistance right after the uh, circuit is not closed anymore? And then what about several seconds later? So this is kind of the opposite of that early part. So the voltage across the resistor will start at its maximum value, and then it will drain to 0. I guess I'm just thinking out loud, but that's kind of what the graph looks like for the at the beginning, where you have the solenoid on top, and then that value drops to 0, and then the resistance on the bottom where it goes from 0 to maximum value. Just something interesting there. I was thinking about. And okay, so at maximum, max current, which is 4.3 amps, times the resistance equals 25.8 volts start, and then at the end drain to 0, so 0, because you know, looks like that. Right, right. that's, before, and then that's whatever. Okay. And then we can check our part D and our part E. So that's really it for this problem. Conceptual part, pretty simple, especially at this state in the game. And knowing formulas for these circuits are important. So I got to take this quiz in a couple. I got to take this quiz tomorrow, so I'm going to make sure I get those formulas into my calculator or in my head or my notes or whatever before I go in. So that's all the videos done, and thank you for watching.